Anya, 15 minutes. And let's put it just here now. And later we will put it in the place.
This is the pointer?
This is pointer and this is to change. You will manage. Okay.
Okay, so good morning. I'm Anya Morvannou and I will present you a study about the hydraulic model to use in vertical flow constructed wetland, and particularly the problematic of hydraulic modeling of French vertical flow systems. I present you first the French vertical flow constructed wetlands. These systems are initially entirely composed of gravel, and reeds are planted in. They are fed with intermittent batches with raw wastewater, and therefore, after some years of operation, a sludge layer develops at the top of the filter, and the filter media turns into a matrix made of a mix of gravel and sludge. The water retention is mainly caused by the presence of this organic matter. So the wastewater passes through the filter, and the pollutants are degraded by microorganisms. After the water passes through the filter, the effluent is sent to a second treatment stage. But nowadays, in order to improve the constructed wetland design, we need to improve the processes and nitrification particularly. So the second stage is no more needed. If we look at a cross-section of a vertical flow constructed wetland, you will observe a strong vertical heterogeneity. At the top there is a sludge layer, implying a high retention water content, and after there is in the gravel decreasing organic matter content towards the bottom of the filter. Moreover, the reeds and the porosity and the network of reed stalks may serve as preferential flow, and through which the water can bypass most of the matrix. Concerning modeling, up to now, vertical flow constructed wetlands are depicted as a porous medium with continuous properties, and water content and pressure heads are at equilibrium. So, often we use the equilibrium model to simulate the water behavior. But when we want to simulate the water evolution in a vertical flow constructed wetland with this model, we manage to model this water content profile at different depth of the filter. But when we carry out tracer experiment with this equilibrium model, we cannot reproduce the tracer behavior in the outflow. Yeah. So the porosity and the network of reed stalks may serve as preferential flow path, and non-equilibrium conditions in pressure head are created between the preferential flow and the rest of the matrix. So the equilibrium model is cannot be applied in this case. So we need to find a model representing the non-equilibrium water flow and solid transport. But which model? The objective of the study is first to answer to the questions how to simulate the hydrodynamic behavior and the solid transport through a vertical flow constructed wetland. We will compare some modeling results obtained with a classical equilibrium model and a non-equilibrium model included in Hydrus 1D. Finally, we will compare these modeling results to tracer breakthrough curves obtained from a tracer experiment. So, Hydrus 1D was applied to a practical case, the first treatment stage of a wastewater treatment plant. This treatment plant is composed of gravel, and a sludge layer has been developed on the top of the filter. We carried out a tracer experiment, and we also measured water contents at different depths of the filter with TDR probes. As the number of parameters in a non-equilibrium model is higher than in an equilibrium model, we decided to use a simplified representation of the vertical flow constricted wetland. It allows to model and understand better each non-equilibrium phenomenon. So the domain was restrained to only two layers, the sludge layers and the gravel-only layer. We used two modeling approaches, the equilibrium model, and the second approach assumes that there is a non-uniform wetting in front, and we use the dual porosity model. In this model, it is assumed that the water flows only in the macropores, called in the mobile region, and no flow occurs in the micropores, called the immobile region. But there is water and solute transferred between the two regions. So here you have the simple representation of the vertical flow constricted wetland and the two modeling approaches. And then for the tracer application, in the first attempt, we only applied one tracer pulse. But during the tracer experiment, we observed that there were some tracer remaining on the top of the surface of the filter. So the second approach was to apply one pulse of tracer and some other pulse of decreasing tracer concentration.
What was the tracer?
Fluorescing. So the modeling results will be compared in terms of concentrations at the outlet of the filter. At this moment, the objective is not to calibrate the dual porosity model, but only to have a better insight into hydrodynamics and solid transport phenomena. Here you have the tracer experiment results. You have the concentrations, the tracer concentrations, and the cumulative percentage of the tracer recovery. The tracer recovery is only about 62%, and it reveals some tracer losses. These tracer losses could be due to the photodegradation of the tracer, or could be due to the adsorption of the tracer on the organic matter, or these losses could be due to the uncertainties on outflow and concentration measurements. So we observed first that the tracer leaves the system from the first batch. Then we observed not only one peak, tracer peak, but several tracer peaks. And finally, we observed the change in the breakthrough curve shape. Indeed, after the first few batches, the tracer concentration first decreases and then increases according to a logarithmic tendency towards an equilibrium value until the next batch. Here you have the modeling results for the equilibrium model and the dual porosity model. On the left for one tracer pulse, and on the right for the several tracer pulses. First, we see that the tracer leaves the system faster with the dual porosity model than with the equilibrium model. Indeed, the tracer leaves the system from the first batch with the dual porosity models, and we have to wait for the second batch to see the tracer with the equilibrium model. Moreover, with several pulses, we observed several peaks, and finally, the shape inversion cannot be observed with the equilibrium model, but it is possible to reproduce this tendency with the dual porosity model. So, in order to simulate the hydrodynamic behavior of a simplified representation of a French vertical flow constricted wetland, we have to use a dual porosity model and to apply several pulses. Now I will talk about the calibration of the non-equilibrium model. In this part, the domain was restrained to 3 layers, the sludge layers and the 2 layers below, which are made of a mix of gravel and sludge. The inlet concentrations were adapted from what we measured in tracer concentrations at the outlet of the filter. We applied 4 batches with decreasing tracer concentration, and we optimized the hydraulic parameters of the mobile and immobile regions, as well as the transfer coefficient, in order to fit the tracer experimental breakthrough curves. So the results of the tracer, the calibration of the model. Here you have the measured and the simulated tracer concentrations. We see that after adapting the hydraulic parameters, we have a good match between measured and simulated concentration. We also see that the tracer leaves the system from the first batch, and we have the 4 peaks as in the experimental breakthrough curve, and we have also the change of the breakthrough curve shape after these first 4 peaks. This represents the fact that the tracer goes into the immobile zone, and then just after the batch, this tracer is released in the mobile zone. If we look at the water contents, it's measured with the cross. I don't know if you see them. The cross and the lines are the results of Hydrus simulation. Even if we only recorded one tracer batch, and even if the variation in water contents are very slow, the model is able to reproduce these water contents at different depths of the filter. So the dual porosity model is able to simulate both the tracer breakthrough curve and the water content at the different depths. So in conclusion, the model, assuming that the flow is uniform through the filter, cannot reproduce the tracer behavior in the filter, but the dual porosity is able to reproduce the fact that the tracer leaves the system at the first batch, and it is able to reproduce the shape inversion, representing the transfer of the tracer into the immobile and the mobile region. So the non-equilibrium approach is the most appropriate for simulating preferential flow in a French-type vertical flow constricted wetland. Now, if you look at the perspective of the study, remind that at the beginning of my presentation, I told that the goal of this study is to accurately model the nitrification in order to improve the constricted wetland design. So now we need to combine your biological module for nitrification and the non-equilibrium model. Moreover, regarding the constitutive layers of the filter, the sludge layer modeling could be improved. For example, by modeling the swelling during the wetting periods and the cracking during the drying periods. And finally, for the gravel mixed with the organic matter, the macropore flow is mainly gravitational. Maybe the Richard equation is not the best for modeling the flow in this area, and it could be a model with a simpler model. On the contrary, the organic matter matrix. In the organic matter matrix, the water flow is slow rather than immobile, and the Richards equation can be used for simulating the horizontal redistribution. Thank you.
Do we have time for one question, please? Okay.
Can you return to your second slide where you show the calibration of the water content?
The second?
The second slide. No, this one.
Yeah.
Which material gives you readings of 0.8 water content?
Yeah, it's a sludge.
Sludge, so it gives you 8?
Yeah, it's mainly water.
And you measure it with the simple TDR?
With the TDR, yes, we had these measurements.
Okay. And the uranium material, did you use uranium for this experiment?
Fluorescent.
Yes.
Fluorescent, yeah. I just wonder if you use a different, more conservative material like bromide or chloride or something like this, if you could also have a better mass balance in your system for the tracer, yes, or maybe you could make more measurements, maybe with the TDR to measure the salinity that's coming from these
Yes.
tracers.
Yes.
Why did you decide to measure fluorescent? Why fluorescent?
Because we cannot use a saline tracer because it destroyed the bacteria. So usually we use fluorescent.
Okay.
And fluorescent is also known to have a visual absorption on the organic matter.
Yeah.
And since we have a lot of organic matter,
Yeah.
we are looking for a tracer which does not absorb.
Yeah, but then you had 60% recovery probably.
Yeah, we had a lot of issues with the outcome as well. That's one of the problems because the flow rates vary a lot. And to have a good device to measure the outflow is not easy.
Okay, thank you.
Thank you.
Next presenter is Susanna.